Good day. Welcome to the first of two videos on chapter 1.6 about planes. Alright, so what have we done so far? We've defined algebraic vectors, and then we used our knowledge and mathematics to define what do we mean by lines, angles, triangles, spheres, and some other objects. Now the next object we want to look at is the idea of planes or flat surfaces. Alright, and planes or flat surfaces are everywhere, alright? So if you look at the surface of a table, that is a flat surface. Now the big question is, how can we define this mathematically? So if we are in 3D, we want a plane to be a subset of 3D with some properties. Now, I'm sure you're going to make a list of things that you would like Father Christmas to bring you at the end of the year. So let's do the same thing. Let's think about planes and let's make a wish list of what properties we would like planes or flat surfaces to have. So, the first one on our wish list is the following. If we have two lines, so think of rulers. If you have two lines and they intersect in a unique point, then we want to be exactly one plane containing both lines. So this is the first one on our wish list. So if two lines and they intersect in a unique point in a singleton, then there is exactly one plane containing both lines. Now our second wish is going to be the following. So you know, if you pierce a line with a plane, most of the time it intersects in one point, but sometimes the line can cut the plane in more than one point. Now if the line intersects the plane in more than one point, then we want the line to be contained in the plane. And this is our second wish. If we have a line and the line intersects the plane in more than one point, then the line must be sitting within the plane. And our third wish is the following, is that if we have 3 points in space in 3D, are they not sitting on the same line? Alright, so there's no line containing those 3 points. Then we want a unique plane containing all three those points. So these are the three wishes. So we need to come up with a mathematical definition so that we have both wish 1, wish 2, and wish 3 granted. Alright, now how do we define a plane? The motivation is in the textbook. You can read it, you can skip it, or you can even ask questions on our question and answer sessions on a Thursday. Remember to post your questions on the discussion board. Alright, but here is the definition we're going to use in 1 to 4. We're going to say a plane in 3D is a set of points of the following form. So P is the set of points of the form R plus S, P minus R plus T, Q minus R, where S and T are real numbers. So R, P, and Q are vectors in R3. S and T are parameters, so they are known or unknown real numbers. But we also need to add to our definition that we want the vector P minus R and the vector Q minus R, they should not be scalar multiples of each other. This is very important. Alright, this is our definition. Now, I can hear what you're thinking. Your first question is, why do we add that P minus R and Q minus R should not be scalar multiples of each other? Why is that part of the definition? Alright, well, let's answer that question. What if P minus R is equal to a scalar multiple of Q minus R? Let's call that scalar alpha. So let's have a look at what will set P be. So set P, I'm going to change my pen color just to be blue. So P will be the following. So P will be R plus S, P minus R plus T, Q minus R, where S and T are real numbers. Now, if P minus R is equal to that, then this will become R plus S. So we're replacing P minus R with alpha times Q minus R plus T, Q minus R, where S and T are real numbers. Alright, but now you can see we can take out a common factor of Q minus R. So this now becomes R plus, if you take out the common factor, we get S alpha. If we take out this common factor, we get T. And so we get S alpha plus T times Q minus R where S and T are real numbers. And now, if S and T are real numbers, then what we have is that S times alpha plus T, that is just a new scalar. Maybe we can call it U Q minus R, where U is a real number. So if we do this, then P will be the set of points of the form. U is a scalar, so it shouldn't have a line on top. So R plus U, Q minus R, where U is a real number. And we know from our work on lines that this is a line. All right? And we know that lines is not planes. And this is what happens if P minus R is equal to a scalar multiple of Q minus R. That set turns into a line. And this is not what we want. We want a brand new object. All right? We've already played with lines a little bit. And so we do not want to redefine what a line is. So if it happens that P minus R is a scalar multiple of Q minus R, i.e. P, Q, and R lie on the same line, then this object turns out to be a line, and this is not what we want. And that is the reason why that is added to our definition. Now the next question is, in our definition, is it true that P, Q, and R are sitting on this object? All right, so we've defined an object to be a set of vectors that satisfies the form R plus S, P minus R plus D, Q minus R. All right, but is this a good object? Well, if we make S naught and we make T naught, then this becomes R plus, if we multiply 0 with any vector, it becomes a 0 vector. If we multiply 0 times any vector, it becomes a 0 vector. And we know that R plus a 0 vector plus a 0 vector, it's R, so it will be sitting on P. So we see that if we define it in this form, and we make S naught and we make T naught, then we get the vector R, which should be sitting in P because that's the set notation definition. Now we can also do the following. If S is equal to 1 and T is equal to naught, then we obtain R plus 1 times P minus R plus the 0 vector, and R plus P minus R becomes the vector P, which is sitting in plane P. So don't get confused. These guys are vectors because they have a line on top, and we're using a capital letter to denote a set. And one more, so if S is naught and T is 1, we get the vector R plus the 0 vector plus T is 1, so we get Q minus R, which becomes vector Q, which is sitting in P. So all three true. So all is true. All right. So this object that we defined this way does contain vector P, does contain vector Q, and does contain vector R. All right. Some more remarks. So we say the following. Vector X is sitting on plane P if and only if vector X is of the form R plus S, P minus R plus T, Q minus R, where S and T are real numbers. So for a line, you only had one parameter. For a plane, you have two parameters. Very important. So a line, you have one parameter. For a plane, you have two parameters. All right? And I made myself a silly rhyme to remember this vector equation. All right? So Peter takes his rands to Spa and Checkers. aka the correct way of spelling Checkers is indicated in the bracket. All right? So Peter, so you're dealing with planes. The vector equation for a plane is X is equal to R plus S, P minus R plus T, Q minus R. All right? So R for rands, Spar is S times P minus R, and Checkers is the silly part where it becomes T times Q minus R. All right? So remember, S and T are parameters, and R, P, and Q are vectors. And again, this vector P minus R is not a scalar multiple of Q minus R. It's part of the definition. All right? So make sure you know your definitions quite well. All right? Again, do not say the following, that the plane is equal to taking your rands to Spar and Checkers. all right, because this is wrong. Because on the left-hand side you have a set, and on the right-hand side you have a vector, and the equal sign is a holy symbol, so that will be wrong. All right. Now, just like lines, the representation is not unique. So there are many, many, many ways of representing a line. And there are many, many, many ways of representing a plane. All right. So guys, please read your textbook and make your own notes. Do the exercises in the textbook in your own handwriting with your own pen and paper. So please do exercises 1.6.3 to 1.6.5. But in this video, I'm going to do exercise 1.6.5. So let's have a look at the exercise. So here we have a plane. The plane is of the form r plus s, p minus r plus t, q minus r, where s and t are real numbers. Remember, a plane is a set of vectors. It's a subset of R3. All right? I'm going to leave it for you as an exercise to show. So this is your homework. To show that p minus r is not equal to alpha q minus r for some scalar alpha. So this is indeed a plane. All right. Now we're going to ask the following two questions. Is the point or the vector 2, 0, 0 on plane P? And is the vector y with coordinates 1, 2, 0 on plane P? All right. So we're going to tackle both of these questions. Let's start with A. All right. Now remember, a plane, you have two parameters. All right. So I'm going to start off by saying, if vector x is on P, then the vector 2, 0, 0 is equal to r plus s, p minus r plus t, q minus r for some scalars s and t. All right. So remember, when you start the question, there are two possible outcomes. Either the point is on the plane, or the point is not on the plane. All right. So we don't know. And that is the reason why in my solution I use the word if. And now let's do the maths. So 2, 0, 0. We are given what r is. R is a vector 1, 1, 0. We don't know what p minus r is, so let's quickly do this. P minus r, that works out to be the vector 0 minus 1, which is minus 1. 3 minus 1, which is 2. 1 minus 0, which is 1. So that was easy. And now we do q minus r. So we do q, we minus r. So we get 1 minus 1, which is 0. 2 minus 1, which is 1. 1 minus 0 is minus 1. All right, so now we continue with our calculation. So we got s times this vector p minus r, which is minus 1, 2, 1. And t times the vector 0, 1, minus 1. All right, so now we got to do the maths. So the first component is 1 minus 2s and no t. And then it's 1 plus 2s plus t. And then we have 0s minus t. All right. And so we should have that 2 should equal to 1 minus 2s. We should have 0 is equal to 1 plus 2s plus t. And we should also have that s minus t. The third component, 0 is equal to s minus t. Please solve systematically. Please solve that it makes sense. So I'm going to call these three equations 1, 2, 3. And now I'm going to explain to myself and the marker what am I doing. So from 1, we see the following. So if this is all true, and from equation 1, we see that s should be, let's have a look, s should be minus, so 2 minus s. Sorry, I made a little mistake here. The first component should be 1 minus s. I was wondering why it looked odd to me. All right, so from 1 we see that s has a value which is minus 1. All right, so if you do the mathematics, it's clear from equation 1, we see that s is minus 1. All right, and now we see from 2 that 0 is equal to 1 minus, s is minus 1, so minus 2 plus t. So t is equal to 1. So t is equal to 1. So t evaluates to 1. So t evaluates to 1, and now we need to check if it satisfies the third equation. All right? So does it satisfy the third equation? So let's check the third equation. So we get that minus 1 minus 1. No, wait. Let me just double check my mathematics. So the third equation should be, pardon me, I think I might have mucked up my mathematics. So q minus r, q minus r, this vector is wrong. This vector should be 0, 1, 1. So this should be 0, 1, 1. And then this evaluates to s plus t. So this evaluates to s plus t. I hope you also see in this video how easy it is to make a mistake, all right? So please double or triple check your calculations because it's going to influence your answer, all right? So we need to check, all right? We need to check. So we need to check. So in 3, the right-hand side is s plus t, which is minus 1 plus 1, which is 0, so true. Now let's summarize. So s equal to minus 1 and t equal to 1 satisfies equations 1, 2, 3. So all of them are satisfied. So the answer is yes. Point X is sitting on plane P. All right, so it's a little bit of a calculation. And you can see it turns out you have to solve 3 equations and 2 unknowns. So typically look at 2 equations, solve for s and t, and once you have a solution, plug it into the third. If it works, then it is on the plane, and if it doesn't work, it's not on the plane. All right, so let's quickly have a look at B. So we're going to start the same way. If point Y is sitting on P, then point Y is of the form, taking your rands to spar and checkers. And it's good to remind yourself what S and T are. S and T are real numbers. All right. Now this time around, the vector that we are dealing with is the vector 1, 2, 0. So it's 1, 2, 0. That is the vector for Y. All right. I'm going to capitalize. We've already done that calculation. So it's 1 minus S. So this is 1 minus s. The second component evaluates to 1 plus 2s plus t, and the last component evaluates to s plus t. All right, so please give it a go. So now these 2 vectors are equal if 1 minus s is equal to 1. So the first components must agree, the second components must agree, and the last components must agree. So again, let's call it equation 1, equation 2, and equation 3, and explain what we're doing. In 1, we see s is equal to 0. In 2, we get 1 plus 0 plus t is equal to 2, so t is equal to 1. That's okay to use full sentences. In 3, the left-hand side is equal to s plus t, which is 0 plus 1, which is 1, which is not equal to 0. So 3, not true. So system has no solution. All right? So you cannot find a value for s and t to make all of these equations true. So what does that mean? That means that point Y is not sitting on plane P. All right. I hope you enjoyed this example. Please try the other examples. And in the next video, we will be looking at some of the proofs regarding planes. Have a good day. Bye.